There. Look, Jeff. Okay. Make that. Okay. All right, guys. Any questions from homework stuff? Just to make sure you're aware, we have lectured through section 4.1. We're going to do 4.2 today. That's crazy. I think for the next test, I'm almost certain that we're only going to make it up through 5.1, which is fine, because if you recall, the first test didn't include 1.2, so that's going to be on this next test, section 1.2. So it's a nice trade-off. We're not going to quite make it 5.2, I don't think. So are you guys really torn up about that? Good. Okay. So the next test will cover from 1.2 through 5.1. You all remember not including chapter 2, yes, because Weird Ash Jeff, I know numbers so good, I did 2 before 1, yes. Me number good. Okay. I'm glad the little man's got headphones on. I do cuss a little bit. I haven't had people bring their kids to class, and I'm like, uh-oh, here we go. All right, so any questions from homework, anybody? Is homework going well then? Is that what that means? You guys are on, you'll find out. All right. Did everybody get their last quiz back? I had a few still here. Oh. Evelyn. Someday, whoever it means. Oh, you did? So guys, there's one idea from 4.1 I want to go back and do. I think I skipped it for some reason. Then we're going to get into 4.2. I got these we're going to play with a little bit later. This is the base 10 stuff here. So, the one thing I skipped, and I'm not sure why, is estimation. I'm pretty sure I didn't talk about this. But if I say, we all at some point have estimated stuff. Did I talk last time about my little old grumpy ass Matthew rant about I hate that? We don't have to calculate tip. We don't have to calculate change, all kinds of stuff. So tip is a really good place for estimation. So what's a good tip to leave for somebody? Okay, 15%. It's kind of like standard, right? So real quick, if I wanted to do 15%, I want to leave a 15% tip. And let's say that the total meal for everybody comes out to be, you can do it, Jeff, $89.12. Right? Now I know we haven't officially talked about percentages, we haven't officially talked about decimals, but I just want to show you a real life example of where estimation might come into play. What does the word of mean in this problem? Not like in the English language, that'd be a little weird. What does of mean in mathematics? Take away? No, yeah. No. Not, especially not in this context.
It is like a portion, or like it's related, like it's a part of it. So.
Oh yeah, that would be if I said something like 7 out of 12 people. So like out of means a proportion, the part of it, yeah. But just of, multiplication, kick ass. Sorry. So 15% of 8912 means 15% times 8912. Now the next level thing, and I know this is a little early for us in this class, but you guys have worked with percentages before. What the heck does 15% mean? Do you guys know what the percent symbol means? In In fact, if you break $1 down, it's how many whats? Break $1 down. It's 100 cents, right? So per cent, per 100. So literally it means per 100. Now this is not why this symbol is the way it is, but if you rearrange it, isn't it the number 100? If you look at the percent symbol, isn't it 1 with 2 zeros? It's not why it's what it is, but we'll go with it. So 15% is 15 out of 100. Of means times. Okay, so if I'm going to try to estimate this, so let me go even one step further. If I want to estimate this, first thing is, what do I do with 8912? Make it frickin' 90. Yes? Do you guys know, so I'm going to say this is approximately this. You guys know how to do like 10% of something? What's the shortcut to do 10% of something? Move the decimal back once. You're thinking about converting between decimals and percentages. Really quick, guys. 10% means 10 out of 100, which reduces to 1/10. So taking 10% of something is literally dividing it by 10. If I divide by 10, I move the decimal back once. Does that sound familiar? Yeah, because our number system is based on 10, so multiplying divided by 10 should be easy. So watch this. It's kind of cool. Kind of cool. Is everybody still with me? Okay. Some of you guys are like, I was not with you anytime. So 10% of 90 is what? 9. Yes? So does anyone know what 5% of 90 is? 5% of something is how related to 10% of something. It's exactly to half. So if 10% of 90 is 9, what's 5% of 90? 450, right? Do you notice if I add these together, I'll get 15% of 90? 10% of 90 plus 5% of 90 is 50% of 90, which is roughly 1350. Just put those together, right? You guys are kind of with me? Screw you, Jeff? You suck? Okay. Maybe. So that's one little place where we used to be able to kind of use estimation. Again, if anybody ever worked in the waitstaff business, it's a good thing that they put the tip at the bottom of the receipt so nobody could go, oh yeah, I just don't know math, and then leave. I'm not good at math, here's $2 on my $158. Isn't that about 20% Bob? No, screw you, dude. Okay. Although, very quickly, my friend Laura, she was a waitress, and I remember I went to her house once and she took a book. My friend was coming back from Mexico, and he was speaking Spanish a lot. So she took a Spanish translation book. We were going to make a joke when we met him at the airport. She opened the book, and like several $20 bills fell out. She said, oh yeah, I forgot. That was my tip. So I put them in there a while back. And I'm like, I wish I had money falling out of my books. Anyway, so they got tipped really well. If I want to get deeper into estimation, what would you guys, how would you estimate 1268 minus 283, for example? How would you estimate this? I don't need the exact answer, I just need an estimate. What would you do to estimate that? You could round. Yeah. It's easier to subtract nice round numbers. How would you round? We can do better. Make it really round.
1300?
Yes.
Minus 300.
So if I round both of them up, what idea does that jive with? I'm using subtraction. If I'm going to estimate a subtraction problem, why do you think I should try to round both parts up? What does subtraction tell you physically? What? Bless you. One number, the other number. Subtraction tells you how.
Oh,
Distance, thank you. I was gonna say, I'm not gonna do this for like 10 minutes. What'd you do in class to watch this guy? You guys remember, subtraction means distance. If I move one up, if I move the other one up, so I keep the same distance. So to make the rounding better, to make the estimate better, if I'm subtracting, I want both numbers to go up or both numbers to go down, right? So if I push them both up, what do I get? 1,300 minus 300 is easy as hell now, right? What's that? 1,000. If I round them both down, Jeff, 1,200 minus 200 is 1,000. Yay! Okay. So you guys are all with me. Okay. So hopefully you've estimated somewhere in your life. What about? Oh, here. What about if I was trying to divide this? Ooh, that looks good. Can you guys tell me real quick? Can you guys tell me? Right, and again, I know I'm bringing in the fractions. We haven't officially talked about fractions, but you know fractions. Can you all write the fraction 6 over 10 down? Can you write the fraction 6 over 10 like below that? 6 over 10. So 6 over 10. Can you reduce that? 6 over 10. Can you reduce that?
Yes.
How do you reduce it? No. LCD would be if I'm trying to put two fractions together. When I have more than one, yeah, here, how do I reduce it? I just...
You can do 3 over half is...
Yes, what factor do the book have? A 2. So if you write 2 times 3 over 2 times 5, the 2 cancels, right? Okay. So my point with this is, what if I go this way? What would I do to go from here to here? I would multiply top and bottom by the same thing, right? So to keep the division the same, I have to, if I make the top go up, I have to make the bottom go up. It's just like subtraction in that respect. If I make one of the numbers involved in division go up, I better make the other number go up to keep the answer roughly the same. So obviously, what would you round 47.983? What would you round it to be? What would you round this to be?
48.
Be better.
50.
50. Yeah, screw it. We're estimating. The whole idea of estimation is to make a problem easy to do in your head. That's why you go for as round of a number as you can get away with. So that's not that big of a difference. What would I do with this one? So we took that, we made it go up. What would you make this become? 5, because if I make the top go up, I want to try to make the bottom go up. Yes? And then what's 50 divided by 5? 10. Can somebody, who's got their calculator right there somewhere? Or who's like, anybody a mental calculator? I'm not. I don't like fish. So, you're, okay, no. So, you know. Can everybody do that problem? Do the problem. 47.983 divided by 4.817. Put the whole damn thing in. Let's see how close our estimate got. I'm curious. Well, then you do it, Jeff. No, you're here, you can do it. I'm going to make you work for me. What'd you get? Oh, sorry. 9.96. Other stuff too, right? Yeah, so this is actually 9.96, blah, 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 blah. Okay. Pretty good estimate. That's a really good estimate, right? Okay. Everything I just said is kind of like the book doesn't say any of what I just said, which kind of drives me a little crazy. This is the most fundamental thing about estimation. What do you think I should do if I'm adding numbers to keep the answer roughly the same? If I make one number go up, when I'm adding, I should make the other one go down. That's related to compensation, yes? So if I round one number up in an addition problem, I should round the other one down to keep the answer roughly the same. Does that make sense? Okay, let me stop for a minute. Same thing with multiplication. Yes? What's 2 times 10? 20. Holy shit. If I make 2 become 4, I have to make 10 become 5, so that it still multiplies to be 20. So in a multiplication problem, if one number goes up, the other number must come down. Are you guys at all with me? Okay. So here's what the book discusses. instead of, good stuff. It does this front end estimation. All front end estimation is if I had to do 482 plus 351. If I'm looking at those two numbers, can somebody identify what you think it means by front end? What's at the front end of those numbers? 4 and 3, okay. So front end estimation just says, only look at the first numbers, 400 plus 300, and what do I get? 700. Now, is that going to be high or low? Why is it going to be low? Because both numbers, I made both numbers go down, yes? So that's going to be a low estimate. Then it says, all right, look at the first two numbers and force them up. 500 plus 400. What's 500? 400? 9. That's a high estimate. You guys see how there's not much to this, right? You can get a low estimate and a high estimate. Why do you think it's important for students to know how to estimate? There's two main reasons. Why do you think it's important for students to know how to estimate?
Subtract in a way.
Beautiful. The most immediate reason you want your students to know how to estimate is if they do a math problem, if they have a way to make the numbers easier and do it, they can check to see if their answer is close. If their estimate is 20 and their answer was 3,847, maybe they forgot to move the decimal back, like they were multiplying, they forgot to move. You see what I'm saying? So it can, knowing how to estimate will catch really egregious errors. You guys with me? Okay, I love you guys. So you guys are barely hanging out. I'm sorry. Okay, not much to that problem, right? Front end estimation. So what about if I am doing a different operation? What if I am, is that coming up yet? I don't know, Jeff, maybe. Oh, that's right. That's right, okay. So if I'm doing multiplication, like 211 times 47, what do you think front end estimation would do? Yes, 200 times 40, that'll be 8, 1, 2, 3. And that's the low estimate. 300 times 50, 15, 1, 2, 3, that'll be the highest. Now in both of these situations, how do you think I could immediately improve my estimate? In both of these. The first one we did, we got a low estimate of 700 and a high estimate of 900. What could you do with those to give one decently accurate estimate?
In the back end, right?
Do it.
Back end?
Oh, I see what you're saying. You, adjust the estimate procedure itself. If I have two estimates, what can I do with those two? Get the average, yes. Right? What's the average of 700 and 900? What's right in the middle? 800. That would be what I would say my guess is. What's right in the middle of 8,000 and 15,000? Do you guys know how to do that real quick? How far apart are 8,000 and 15,000? How far apart are 8,000 and 15,000? 7,000. Cut 7,000 in half. 3,500. Add 3,500 to the low. Okay. I always feel like I throw so much at you guys, but if I'm trying to average two numbers, one way to do it is just how far apart are they? Cut that distance in half and add that to this. Of course you end up in the middle. All an average of two numbers is trying to do is try to be in the middle of those two numbers. Yes? So if you see how far apart they are, cut that in half, you're in the freaking middle. Yes. What is 211 times 47? People with calculators right there. Wait. Do it again.
9,917.
9,917?
Yeah.
Okay. So our estimate's not terrible. It's not great either. Are you guys all with me? So if I say use front end estimation, you have to get a low and a high, and if you average the two, that's like extra. That's like a little extra thing we did. But to me, it only makes sense. Now, just to make sure, I want you to take this number and can you round it to the nearest tens? What's the nearest tens? You guys remember rounding, right? So what number's in the ten spot? What tells you what to do with that number? The next number, right? So it's a 4, so what do? Oh, I see. Okay, keep it the same, right? Yeah. Because currently at 94, you can either round it down to 90 or round it up to the next 100, right? So this would go 4190. Is that cool? Yes.
What does the top say?
Oh.
Sorry.
Hold on. Round to nearest. Round to nearest tens. Round to nearest hundreds. What would that be? Hundreds? Sure, Jeff. I'll keep that way. Hundreds. Round to the nearest hamburger. Round to the nearest. Cool fifi. No, round to the nearest hundreds. Let's pretend like that's what that says. Yeah. So real quick, y'all agree with me 190 is in there. Would y'all agree with me 190 is in there? So I could either round to 190 or I could round to 200. And 194 is definitely, I'm sorry, not 100 or 200, yes. I could either round to 100 or 200. And 194 is so much closer to 200. Everybody freaks out a little bit when there's a 9 in my rounding problem. It's not that big of a deal. Okay. What about, real quick, what about this here? I know I'm bringing up decimals again, but round to nearest, my God, Jeff. Okay, I have to have one issue. Either I can spell but I can't write, or I can write but I can't spell. I can't do both. Round to the nearest, hundredths. What number, well, it's 3 of the same number. What number's in the thousandths place? What number's in the thousandths place? Yeah, because what place is this? Tenths, because it goes tens, ones, I keep dividing by 10. 1 divided by 10 is 1/10, that's in the tens place, hundredths place, thousandths place. Okay. Alright, I like it. And when I teach fractions, make sure nobody sits in the front row because you'll be in splash. So if I round it to this place, what does that tell me to do? Yeah, so 4.4. 5. I like it. You can put a 0 on there. Math says it's the same thing. If you took any chemistry, you're talking about significant figures and stuff. I'm not going to do that. Alright. Now real quick, just stay with it. What if I want to round the same number, but I want to round it to the nearest tenths? So real quick, and you're fine. Everybody does this. It's not a dominoes thing. You can't say, well, this makes that a 5 and that makes that a 5. It is what it is. Find the spot. What's next to it? That's a 4, so that's not good enough to push that up, so it stays. Yeah, but you're perfect. Don't get me wrong. Everybody makes a mistake because their brain sort of sees that as dominoes. That makes this, that makes this, that makes this. No, 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 no. It's immediately what's next to it. Yeah. So that would be 4, 4, 4. I'm sorry, what did I say? Tens. 4, 4. Okay. So very exciting. Okay. Last little thing. Let me see. Somebody actually just asked me a question about this. And I think I'm gonna have to. Well, I have my pencil sharpener, but I don't have. Can I borrow your? Was it you that asked me the calculator that you were using? Yeah. Thanks, man. Appreciate it. If I did in the calculator, if I did 159874589 times 5894 blah blah blah, I get this. What the shit does that mean? Obviously, you guys you didn't see what numbers I put in, but I put big numbers in, correct? There's no way in hell the answer is 9.4, right?
18 trillion times 3 trillion is 9.
No. So what does this mean? What's it mean? What's this last bit mean? Times 10 to the 18th. When you multiply a number by 10, what happens? The decimal moves once. So how many times do I have to move the decimal? 18 times. So you move the decimal 18 times in the positive direction because it's positive, and that's what the actual answer is, yes? And in fact, the calculator screen is only so big, so it can only show you so many digits. Okay. That's one reason why it does that. We don't want these calculators that are like that wide or something. No, I'd rather do this. Let me think. There was something else I was going to show. Oh, no, it's okay. That's one little thing that might come up in the homework. Thanks. You should have said, "Come on, math boy, you don't have that calculator." I'm sorry. Okay. So now let's get into, that's 4-1. That's the end of 4-1. That was one little bit, I don't know why I skipped estimation, but I just did. We got into 4-2 a little bit last time. You're stuck there forever. I got you. And I think what we did last time was we did this problem a few different ways. Yes? Okay. And that was infinitely interesting. So we did it with like base 10 pieces, just to remind everybody. So we did it like 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 1, 2, 3, 4, 5. And then we just considered what would happen if we put those together. So we would get, we got 13 of these, so like 10 of these, yeah, you can do it. These 10 here would become another 1. So now I've got, did I just draw that? Yes, I did. So then I have 4, 5, 6, 7, 8, 9, 10. Those 10 would become a flat. So then I have a flat, I have 1, and I have 3. Okay, so that's what we did with paper and pencil last time. I've got those pieces here. We're going to mess with those here in a minute with subtraction and division. So this is the first direct work your students would do with a problem like this. Like you could talk about 7 plus 4, and you don't need base 10 pieces for that. Yes? You can count on from 7, you got all these different things you can do. But when you start talking about 70 equals 35, we're going to need some help. We're going to need some stuff to look at, because that's too much to keep in my head. Yes? And I talked about this last time. What idea just naturally came out of messing with physical objects? What mathematical idea just came out? Carry the 1. In fact, carry the 1 happened twice, right? Because if I do this by the standard algorithm, what happens? 8 and 5 is 13. 8 and 3 is 11. There. We normally don't do that last thing, but just to show you, that is carrying the 1 over there. Okay. So we kind of bleed over into the next place up. But it's kind of, again, I've said this before. I hope somebody out there, it's really cool that a mathematical idea like that just naturally happens. The students don't even know they're doing it. It's like, oh, if I stack these, it makes one of those. Oh, they just carried the 1. They don't even know it. Okay. I talked about what's called the chip abacus. Did I talk about this? I can't remember if I made it this far. Let's see if you guys understand this. This is alright, so today we're going to be talking about, oh, you're going to be so excited. It's going to be so, we're going to talk about these intermediate algorithms to kind of step from pure physical manipulation to pure mathematical computation. Okay, that was a lot. A world of pure computation. Okay. I'm going to represent those two numbers, but I'm going to use, I'll show you. Here's how you work with the chip abacus. You just put in there 78 and 35. 78 would have 1, 2, 3, 4, 5, 6, 7 tens. 1, 2, 3, 4, 5, 6, 7, 8 ones. 35, 1, 2, 3 tens. And then 1, 2, 3, 4, 5 ones. We stop for a minute. So we do the same thing. So this, all right, let me show you what we do. We do exactly what you might think we do. We notice that this becomes, I end up with 10 of these, and I end up with 13 of these. I think I counted correctly. Yes? Are you guys still with me? This is crazy exciting, I know, and I appreciate everybody maintaining their calm. This seems like such a small step from this. This, I know I'm drawing it, but it's going to be sitting on their desk. This they can draw, but it immediately looks like this did. Yes? And then, I'll do the same kind of thing. These 10 bleed over into this section. So there's none of these now. And then 10 of these, you've done such a great job here, Jeff. 10 of these bleed over into this section, so now there's 3 here. Let me put you down there. So 1, 13, right? 1, 13. So it's a tiny step away from the physical manipulatives. You can see carry the 1 in a different kind of way, but it's related to the physical manipulatives. You're trying to carry them ever closer to understanding the full thing we did here. And then finally there's this. Let me show you this. This is kind of nifty. Place value. This one is the niftiest one, I think. It shows you the bleed over I talked about. So I'm going to add 78 and 35. What's 8 plus 5? Holy shit. And 7 and 3? Holy shit. So there's the bleed over of this. So if I kind of stack these up, I get 113. So like this is the 1 spot and this is the 10 spot, yes? So there's this bleed over of the 1 because the 3 is the only thing that could be in the 1 spot. Now that one's a little bit trippier, but this is what I want you to see when you do that. 13, so that bled over into the 10 spot. 10, so that 1 bled over into the 100 spot. Okay. That's definitely getting closer to carrying the 1. It still is not carrying the 1. It's still 8 and 5 is 13. But when I write 1, 3, the 1 is in the next place. It's bled over to the next place. Okay. Love you guys. So then, all right, these are all still visual ways to do this. So here is intermediate algorithm 1. Let me show a different example. I'm getting tired of 78 plus 35. So if I want to do 472 plus 298. Now, watch the difference between what you're used to doing here and what we're about to do. Well, what's 2 plus 8? This is kind of coming right off of that last thing we just did. 2 plus 8, you're not going to believe it. It's 10. What is 70 plus 90? 160. And what's 400 plus 200? 600. And again, this is even better. Now you can see directly. We haven't carried shit. It just happened, right? The 10 made that go over there. The 160 made that 1 go over there. So now I get 770. Thankfully, that's the right answer. Okay. Is that the standard algorithm? No, it's intermediate algorithm 1. It takes where you leave off from the the base 10 pieces, the chip abacus, and then you come to intermediate algorithm 1. They're not carrying the 1 yet. And I think parents don't stop to think carrying the 1 is a very trippy thing. It's not trippy to us because we've been doing it our whole life. But it is trippy. Intermediate algorithm 2. How many of these are there? There's only like 11, so I'm joking. There's 2, and then there's the standard. This one's kind of funny to me, but I'll just show it to you. This one's really silly. 2 and 8 is 10, 7 and 9 is 16, but since they're over 1 spot, I put the answer 1 spot over. And then 4 and 2 is 6, so then I get 770 still. So all I did there, 2 and 8, I'm going to put the answer in the spot and the 1 goes next to it. 7 and 9, I'm going to put the answer in the spot and the 1 goes next to it. Are you guys with me? And then where's 4 and 2? It's in this spot, so I put 4 plus 2 is 6. Let me do it again. 2 and 8, the answer starts here, and if there's any more to it, you put it over there. 7 and 9, the answer starts here, and if there's any more, you put it over there. 4 plus 2, the answer starts here, and there's no more extra, so there's nothing next to it. Okay, let me stop for a minute. I love you guys. This is, okay. This is where you really have to recognize what does that step accomplish? What do you want them to be able to do eventually? You want them to look at 7 and 9 and think 16, yes? And then we want them to carry the 1, don't we? We don't want them to look at 7 and 9 as 70 plus 90. We know that's what it is, but when we're doing the problem, if you just added the damn things the way you know to, you're not going to look at it as 70 and 90, are you? You're going to look at it as 7 plus 9. This 70 plus 90 is 160, 400 plus 260. This 2 and 8 is 10, 7 and 9 is 16, 4 and 2 is 6. That's one step closer to our standard way of doing it. Yes? You have got to build, move forward. Build, move forward. You can't just jump to the end because they have to have something grounding that tells them why that makes sense. And then, of course, finally, standard algo. I think I'm going to write algo instead of algorithm. Is that cool? The standard algo. How does it work? So 2 plus 8, 10, carry the 1. 8 and 9, 17, carry the 1. 5 and 2, there. But can you see how everything you did before this leads to this? The carry the 1 is coming from what they saw physically, what they saw with the other previous intermediate steps, that bleeding over of that 1. So this is just a shortcut now, right? They're like, we're doing the same thing we did before, we're just using a more concise way to write it. Okay, Maybe. And I need you guys to appreciate, if you're gonna teach these people, you need to appreciate the need for this. Because we ain't born knowing this crap. We ain't born knowing the number 4. So how in the world are we supposed to be born knowing how to add 3-digit numbers? Holy shit. That is weird. Okay. Now here, can somebody tell me if you've ever seen this before? This is called the lattice method. Not the lettuce method, I'm sorry. That might be a diet somewhere. The lattice method looks like this for addition, because there's one for multiplication. If I want to do 472 plus 298, you draw a box. Just like that. You guys with me? Kind of like line up the 2 and the 8 to be over this, the 7 and the 9's over this, and the 4 and the 2's over this. Is everybody with me? Does this look familiar to anybody? Yes? Where have you seen it before?
I did it as a kid.
You remember doing it as a kid? Your memory's so much better than mine ever was. Did somebody else say they had seen this before? Okay. Yes, you've seen it? Was it more recently or when you were little?
No, I did it like 2. I was learning how to add.
Oh, you remember from when you were first learning? Neat. Okay. I'm so jealous. I don't remember much of it. Do one of you guys remember how this works? What's 2 plus 8? 10. Look, you write the whole damn number. Isn't that nice? What's 7 and 9?
16.
That's crazy. And then what's 4 and 2?
6.
0, 6. Yes. Do you see that? Now watch this. Go diagonally. Yes? 0. 1 and 6 is 7. 1 and 6 is 7. Do you see that? That's the right answer, correct? Thank the gods. I mean, yay. And you can see, again, that's the carrying. When you go diagonal, that was here, but now it's there. That was here, but now it's there. That's the carrying of the 1. This is not a standard thing that's shown, but some school systems kind of like to show this as another intermediate step. The one that's for multiplication is really tricky. So here, can you guys try to do the lattice method for this? Go ahead and try to attack that with the lattice method. Lattice method. It sounds like a yoga thing or something. Breathing exercise. So let's see, 5 and 9, 14, 8 and 2, 10, 6 and 7, 13, 4, 1. What kind of 4 is that, John? 4, 1. 14, 14. And then you can double check it. That's the answer. Thank the gods. That's pretty cool, right? It's not bad. Okay. In fact, it's not that far from what we do. But it can be confusing with really long numbers. You get a little lost in the sauce. And if I'm trying to add like 3 digits, this method really kind of goes to hell. Because then you're carrying within it sometimes. Anyway, okay. So this method is okay. It's not too bad to show. It's another way to see how carrying the 1 happens. But it, yes, sorry.
Why is it not 15 instead of 14? This is 1 and 4 to 5.
Oh, well, see, so this is 4 here, right?
Yeah.
1 plus 0 is 1, 1 plus 3 is 4, and then 1 plus nothing is 1. Yeah. You're good. Okay. Now, let's talk about subtraction. I'll go for subtraction. Yeah. Yeah, I think I'll do this instead. I'm not gonna, let's do this. 2, 4, 6, 8, 10, 12, 14, 16, 18, 19. Did somebody just step up 20? So I got 20 people. All right, let's do, yeah, that works beautifully. Wait a minute. That works beautifully. Let's go into groups of 4. Let's see. Did I get that right? Yeah, sure. Let's see. Yeah, okay. So I want, yeah. So 1, can you guys just get together into groups of groups of 4, yeah. So I want 5 groups of 4. Can you guys just get together in groups of 4? Let me know if you need some help. You guys, so obviously I think before my, that's, you guys, and 2 more people come over here to make a group of 4 back there. Little man here, I don't know if he's gonna, whoever this person is, they can come back there and work with you guys. Yes? Okay. Where are we at? Okay, so you guys got 3, 4? 4. You guys got 4. Can you 2 go over and work with them over there?
I know, I'm like doing everything in every
Thank you.
color. It doesn't even got.
You guys go, we'll wait for this person to come back.
You got you back here.
What's up? Oh, yeah, I'm sorry. Thanks, man. Work with those people right there. Can everybody please represent the number 235? Represent the number 235.
Bless you.
All right. Yeah, you gotta crack that bag open of the little unit dudes. No, okay. So 200. Zoom out. 230. Oh, scheisse. Oh, shit. Oh, these are these like brand? No, they're. I'm gonna. These come open? No, you have to actually tear into them. You need a. Maybe the other side came open. So we'll do it. Alright, so 235. Again. So everybody's got 235?
Yep.
Alright, so I want you to do 235 minus 147.
Or you can't add more things to it. Oh, are you wanting us to show it? Oh.
Yes. Try to do 235 minus 147 with your pieces. There's no need to represent 147 by itself. You're subtracting 147. 235. So we're going to do the takeaway approach. Since we all know how to do that, you can consider what you would do and see how it would translate to these pieces. But remember, your students don't know. They don't know how to borrow. Yes? Oh.
good, Jeff. You missed everything.
Okay. All right, guys. So, last couple things for today. It's gonna take us a little while, so don't get too excited. Everything's gone. Here we go. Oh, there you go. So, guys, real quick. Yeah, let's do this. 333 minus 158. So to show you less physical, more computational approaches. So if I do this is what they call a chip abacus. So there'll be 3, 3, 3. I want to subtract 158. So now we're getting one step away from the purely physical objects that they can manipulate, the flats and the longs or the sticks or whatever, and the lemon drops, whatever that. So here, there's going to be a couple steps. So if I want to subtract 158, I could subtract 1 right now, but I'm never going to be able to subtract 50. I'm never going to be able to subtract 8, right? You guys with me? So to clean this up a little bit, I'm going to borrow one of these and put it here. So now this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, with the 3 that was there already. And I'm going to borrow one of these, put it over here, and that's going to be the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, with the 3 that was there already. Whew. You can see how this gets really messy. But now if I take 1 away, chunk, and I take 5 of these away, chunk, and I take 8 of these away, you can do it, Jeff. Can you? Maybe. Here's 8. Chunk. See what I got left. I got 1. I got what looks to be 7. If I kept track of everything, 1, 2, 3, 4, 5. All right. Is that the right answer? Maybe. Okay. Again, I really appreciate you guys. You're all keeping very calm. Is that the right answer, guys? Yes, it is. Okay. And then you've got what I prefer rather than this, especially when you start dealing with numbers like this, is something kind of, yeah, Jeff, let's just say kind of in the middle, where you represent the number. And this kind of leads over into the next algorithm. You make this a 2, which makes this a 13. You make this a 12, which makes this a 13. Let me see if you guys are with me. So effectively, I'm doing the same thing I did with the chips, but I'm just doing it directly with the numbers. 1 of these is 100, so now I've got 30, no, I've got 130. Let me say that again. When I borrow one of these, that's 100. So when I add it to these 30, that means I got a 113, yes? Then I borrow one of these, leaving me a 120, that's 10, and 3 is 13. So some of you guys might recognize, this is if you forget to change to A, B, C, D when you're converting to like base 14 or something. So obviously, this is one spot, this is one spot, this is one spot. So now I can take 100 and, 58 away. So minus 1, minus 5, minus 8 is 175. And do you see how I need you to, I'm looking place value, and if I look place value wise, and I'm writing the amount that borrowing a 1 would leave me with. Gosh, I wish I knew English better. It's my first one. Does this make any sense? This is a really cool idea. I'm not writing the number, I'm writing what I would have in each place after I have borrowed. And then I've got 3 little simple subtraction problems. Do you guys see that? So we've taken this horrendous problem, really, 333 minus 158. That's not, was it 158? Okay. That's not like an easy problem. And we've converted it into 3 very simple, at most 2-digit little subtraction problems, yes? Which is effectively what borrowing does. Just not like this much in your face. And if you look at the actual algorithm we use, I would borrow, so if we do this, we borrow from here, then we borrow from here. And there's the 2, the 12, the 13, yes? Okay. But it takes a little bit to get to the point where you do it all kind of like in one compact go. So the weird paradoxical thing about teaching really simple stuff is that you guys have to understand it to a point where you're ready for any weird questions your student asks you. And also that you really understand what it takes to understand how to do this kind of problem. So that's what I try to do, is to show you deeper what's going on. Here's a little, okay, this is a little side note, but I want to show you, this is kind of funky. This is called subtract from the base. Okay, I'm not going to really worry too much about this, but I want to show you this once. So say I want to do this. Now normally I would subtract 6 from 2 and I go, I can't do that, so I've got to borrow. You guys with me? But instead we just go, no, 300 is in there. Do you guys see 300 in there? And I'm subtracting 60. That's part of what I'm subtracting, correct? So what is 300 minus 60? 240. Now, what is 20 minus 4? So I've already subtracted 60. The only thing I have to subtract still is 4. Is everybody with me? So I've got a 20 and I've got a 4. So what's 20 minus 4? 16. And then what number is still there that I started with? We didn't do shit with him, right? So what do I get? 259. And that's what it is. Let me stop. I don't know if you guys are really with me. I'm almost certain nobody's ever saw that before. So that is breaking out. All right. I really appreciate that. I get really excited about weird little shit like what I'm about to try to explain. Right? It's okay if you don't. I want you to understand. We are so stuck in the algorithm. If I ask you to subtract that, you guys are automatically going to start to borrow. And there's nothing wrong with that. That's the way we do it. But if we step outside of that shit and go, well, there's a 300 minus 60, okay, that's easy. And there's a 20 minus 4, that's easy. Because that's all in there. That's all part of the problem, correct? 300 minus 60 is part of what it's asking me. 20 minus 4, that's part of what it's asking me. And then I got an extra 3. So if I just combine all those, I get the actual answer. Maybe. And again, I'm not going to spend more time on that because that's a little side note. So just in case, though, if you work at a school where this is part of the curriculum, you can see what it's all about. Okay. Somebody remind me. So let's go back into multiplication. So I've already shown you how to do it with base 10 pieces. What is the most fundamental way to do 3 times 213? It's basically, we already talked about it. But what's the most fundamental way to kind of like represent 3 times 213? Yeah. So you got 3 213s. So I do. So I got 2 1 3, 2 1 3, 2 1 3. Add them up. 6 3 9. Is that cool? I'm kind of marrying the chip abacus way with the place value way. We've also got stuff we've talked about before, like the right to left stuff, or is it left to right? Left to right. This kind of thing where you make it a 200 plus 10 plus 3, so then you distribute the 3. 3 times 200 plus 3 times 10 plus 3 times 3, and you still get 639, thank God. Now, one step closer to our standard algorithm would be this. What's 3 times 3? 9. What's 3 times 10? 30. And what's 3 times 200? 600. So then you still get 639. Okay. And then, oh God, that's where I did this. Yes, okay. So that kind of feels like what we did earlier with addition. Same kind of idea. Written very differently than we're used to, but that's kind of an intermediate step. So let me kind of drill down here. Let's do this problem. Intermediate algorithm 1. So that's me doing like 23 times 15. So here we go. Here's the full technical idea of kind of like the first way to look at just pure computation. No physical parts, nothing like that. 23 times 15. What's 5 times 3? 15. What's 5 times 20? 100. What's 10 times 3? Is everybody with me? 10 times 3? 30. And what's 10 times 20? Oh, put 15, that's right. Okay, that's all right, Jeff. I had put something else before, I'm like, what am I doing wrong? No. So then you get 345, is that cool? Okay, too crazy. Intermediate algorithm 2 would do this. I'm going to do 5 times 23 here. What's 5 times 23? 5 times 2 is 10, 5 times 3 is 15, so that'll be 115. And then here I'm going to do 20 times 10. 5 times 23, not 20, Jeff. Let me make sure I'm looking at, oh yeah, I see what I'm doing. I had a different problem here a second ago. 5 times 23 and then 10 times 23. So 5 times 23 and then 10 times 23. 10 times 23 is 230. And when I add those together, I still get 345. So that still isn't our standard algorithm, but we're one step closer. And just to point this out, this is the one that we would carry. Right, so if I do this the way that we do it normally, what's the standard algorithm? 23 times 15. 5 times 3 is 15. Carry the 1. 10, 11. And then I put, I don't know, do you guys put a 0 there when you do this?
Yeah.
I've noticed that some schools don't teach the 0 there, it just leaves it open, which is funky to me. 1 times 3 is 3, that's crazy. 1 times 2 is 2, that's insane. And then I still got 345. So this 15 piece is here. Yes? And then this 100 piece, of course, is here. And that's related to the carrying that we had to do. So I think let's see. Yeah, we'll do that. I want 2 more things to show you. The lattice method for multiplication. Okay, this is going to be a little bit tricky. So let's do 3276 times 27. So the way we set this up is a little bit different. I'm going to put 3, 2, 7, 6, and then 2, 7. Yes.
Just for a second.
Oh, sure. Yeah. This is really kind of nifty because it breaks this really kind of gross problem where we have a lot kind of going on at once, and it just breaks it down to all the parts that are involved. What is 6 times 2? That's right. 12. What's 6 times 7? 6 times 7. 42. 7 times 2. 14. 7 times 7. 49. Thank you. 2 times 2. 4. 2 times 7. 14. 3 times 2. Jeff, you forgot one. 6. 3 times 7. 21. So make sure each of those little boxes is split into 2. And then you do the exact same thing we did earlier for addition. But let's see if you catch the one little piece that's a little bit tricky. So I go across, there's 2. 2 plus 4 plus 9. You guys see that? 2 plus 4 plus 9 is... All right, let me stop. Let me make sure everybody's with me. So both lattice methods, the last step is to go diagonally and add all your parts. Yes? So that very first and the very last number are going to be kind of like on their own. Or little 2 has nobody, or little 0 that has nobody all. So 2. 2, 4, 9, 15. So I have to carry in this. 2, 4, 9, 15, carry the 1. 2, 6, 10, 14. Is everybody with me? 2, 4, and 9 is 15. Carry the 1. 2, 6, 10, 14. Carry the 1. 2, 3, 4, 8. No 1 to carry. 0 plus 6 plus 2 is 8. Yes?
I'm so sorry, did you go over that?
Hell yeah. 2. Is anybody with the 2 diagonally? No. Poor little 2's all by himself. 2, 4, 9 diagonal here, right? Do you see that? So then I add those, I get 15, 5, carry the 1. 1, 1 is 2, 4, 4, 4. Those are all in a line. Those are all in diagonal, yes? Carry the 1 here. I carry the 1 here from the 15. These are all in a diagonal line here. Is that cool? Okay, so then I get 2, and then 4, 4, 4 is 12, plus 2 is 14. 4 goes here, carry the 1. Look diagonally again. 1 plus 1 plus 4 plus 1 plus 1 is 8. Oh, there it is. No 1 to carry. And then diagonally again, 0 plus 6 plus 2 is 8.
And then you just have it, okay, thank you.
You're welcome. Yeah, Megan, you're fine, man. This is such a weird, if you've never seen this before, it is weird. But again, do you see how all of the carrying, all of this, it all happens internally? You don't have to keep track of it. It's all there in your face. Now, when you're adding, you do have to carry the 1. But when they get to multiplication, they should be decent with addition. They understand carry the 1 by the time you get to this. Is that the right answer? Yes, cool. All right. I forgot to check, so I was like, I don't know. I hope it is. Okay. So very last thing for today. Dear God, Jeff, we've put up with you so much. We should get paid. I understand. I'm sorry. This is where I remembered I was silly. I should have made you guys do this problem when you had the parts, but you didn't have enough parts anyway, so it's okay. If I want to do 5/16 divided by 3 using these pieces, so we're going to draw. How the shit would you do that? What the shit? So dividing by 3. Why is 6 divided by 3 2? Why? I'll take anything. Why is 6 divided by 3 equal to 2? That's crazy. Say it a different way. Somebody say it a different way. Why is 6 divided by 3 2? Somebody else say it a different way. Grace is doing it. Is it
it takes 3 2s to make 6.
It takes 3 2s to make 6, right? Another way to look at it is how many, if I'm doing 6 divided by 3, a way to ask myself is how many groups of 3 are in 6? For every group of 3, I count that as 1, yes? So 6 is 2 groups of 3, 1 and 1 is 2. You guys with me? That is the most fundamental way to look at division. So if I represent 516, 516. Okay. 516. How many groups of 3 are here? How many groups of 3 flats? You can do it. There's one group of 3 flats, yes? So that's one of these. These guys, what do I have to do with these guys? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What was your favorite part of class? Watching this fool count to 10. How many groups of 3 are here? Now, we could sit here and circle them until we go crazy, but don't I have 21 of these? How many groups of 3 are there in 21? But your little person that's first learning this can sit there and just kind of like circle these, or if they have the physical pieces in front of them, they can group them in groups of 3. So there's 1, 2, 3, 4, 5, 6, 7. Yes? 7 groups of 3. Is that cool? You guys with me? So, if I had 3 sticks and I had to divide it amongst 3 people, how many would each person get? 1. So for every group of 3, I represent it with 1. That's how I divide by 3 visually. Dividing by 3 is trying to say how many groups of 3 are there. So for every group of 3 somethings, I represent it as one of those things. Because that is one group of those 3. Does that make sense? What I literally just did at the top, this thing that looks like a weird UFO trying to pick up the skinniest cow ever, that is 30 divided by 3. That's what that means. Yes? What does each stick mean? 10. So that's 30 divided by 3 is 10. You guys agree? Is that better? And again, a lot of this shit is like, it's really weird when you have such a basic idea and then we're talking about it in a completely different way than you're used to. It's fine for it to not make immediate sense. Okay. Your students, though, really quickly, this is the tricky thing for you guys. Your students are going to be coming from the other side. Everything is trippy to them. So they're going to connect to the physical, whereas you guys are going this way. You're like, I know how to do this shit. How do I do that shit? And they're going to be like, I don't know anything, but I like to play with that shit. So you're coming at this idea from 2 different sides, which is weird. God, I talk a lot. I'm sorry. Okay. So there's one group of 3 of these, so I represent it with 1. We broke those down. 7 groups of sticks. So there's the 7 sticks that represents each of those groups of 3. What do I have? And then I have none of these left over, correct? Yep. How many groups of 3 dots do I have? Yes, 2. So what do I get? 170. $172. Is that cool? What is 172 times 3?
516.
If we're right, it's 516. So I'm gonna. That's correct. Okay. Do you guys see how I? Let's do one more. I know I said that was the last one, but too bad for you. I lie so much. If I talk so much, you know I gotta lie sometime. 631 divided by 4. $631. How many groups of 4 flats? One group of 4 flats. Take these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Go, Jeff. How many groups of 4 here? 1, 2, Good Lord, Jeff, what have you done? 3, 4, 5. 5. Thank you. What do I do with these? Break them down. So I got 31 here, correct? How many groups of 4 are there? 7 groups of 4. And they could circle it, they could put them together, whatever. So I get 7, 1, 2, 3, 4, 5, 6, 7. How many get me left over? 3. So if I circle 7 groups of 4, there will be 3 left over. So this will be 1. What is that? 5, 7, remainder 3. The remainder is literally what's left on the table. So then the remainder becomes physical. Yes? The remainder is just the little parts that didn't get to go in any groups. Aw. But they get to be next to the big ass R. Big ass. So we will be writing big ass R for now because we haven't officially talked about fractions. And maybe. So literally, one of the best ways to physically look at division is if I divide by 4, I'm asking how many groups of 4 are in this thing. If it's not an even group of 4, then we're going to get a remainder, yes?
How many dots on the right?
I kind of gave up, but do you see these 3 here?
That's 30, right? So 30.
So then I have 30 dots, and then the one that was already there. So I have 31 dots.
Okay.
Yeah. And the reason it's 31 and that's 31 is because 4 times 15 is 60. So the 600 is taken care of here. We have exactly 31 dots. All right, that's plenty. I've thrown a lot at you. That's plenty. We'll stop there. Don't forget, quiz Tuesday, 3233. What we just did today is 4-2. Next time after the quiz, we'll do 5-1. That's as far as the test is going to go. I'll have the practice test next Tuesday. Review is next Thursday. Test is the Tuesday after that. Oh my God.